thanks a lot for the organizers for having me, and I'm very sorry about forgetting to send the title. It's going to be transport in strongly interacting Fermi gases. If you allow me, even though this is an optical lattice workshop, I think we can gain a lot of intuition from the bulk, and also when we are after trying to detect states of matter using transport, it would be good if you just train ourselves on anything, like, and a bulk superfluid is good as anything, right? Generally, these fermions are a wonderful thing because they make up everything we exist from, so they make up nuclei. Of course, these guys, neutron stars, are very far away, not so easy to touch, so we don't know quite so much about them. And white dwarfs, okay, same thing. High density superconductors, even though we can sort of touch them, very nice, human scale, we don't understand them. So of course, that's where the cold gases might become helpful. And I think we are really at the point right now where the experiments, I don't want to insult anyone, but I think they are going beyond what is capable currently on classical computers. So you can prove me wrong, but I think it's a very exciting time right now to be looking at these atomic systems. And one example, and maybe the hardest example, to tell you how these cold atoms could be very useful is transport, and especially DC transport. So really the DC conductivity, which is the defining thing that defines states of matter, insulators, conductors, that is the hardest to calculate. So there's, in general, for strong interactions, as we heard, no simple quasi-particle description. Perturbation theory fails. We would love to do some real-time evolution of our Hamiltonians, and then we realize we cannot evolve for long enough, because if you want the zero frequency conductivity, you better go to infinite times. That's of course tough. You can start with Monte Carlo, which is basically done in imaginary time, and then you have to realize, wait a second, already that fails due to the fermion sign problem. If you want to get transport out of it, you need to do some analytic continuation from that imaginary time to real times, and that is very difficult at very low frequencies. So these are all kinds of issues that make it very difficult to calculate these things, and so we don't know the transport properties of, for example, the Hubbard model, and we need to check what analog quantum simulation using cold Fermi gases gives us. Just one issue that was on the previous slide I wanted to show here with maybe the simplest system I can think of that shows these strong interactions. It's a single spin-down atom that I throw in a bath of spin-up fermions. This is the Fermi-polaron problem, so it's a single spin-down, sort of polarizing the surroundings. And at low temperatures, we know this forms a beautiful quasi-particle. So actually everything should be good in terms of calculating transport coefficients and all. It's a Fermi liquid. But as you heat up this polaron, it becomes, well, what you could call an incoheron. That's an invention. Doesn't exist really, but you see it becomes very broad on the order of the Fermi energy, which is the largest energy scale in the problem, and you can no longer speak of a well-defined particle. So the moment you're trying to, for example, do spectroscopy on it, it gets already knocked by some majority atom. You could call this quantum pressure broadening if you wanted to. This is a plot that shows this broadening as a function of temperature. So here you have the full width half maximum of the spectra on the previous slide versus the temperature normalized by the bath temperature, normalized by the bath majority Fermi energy. At low temperatures, you see what could pretty much look like a quadratic dependence, as you expect from the Fermi surface starting to soften and giving rise to a lifetime that's quadratic in temperature. But then, at some point, once you're hitting temperatures on the order of the Fermi temperature is the only scale in the problem, and the broadening is on that order. So this is the complicated incoherent soup. you could also say that this is showing you what happens near the quantum critical point that controls that problem, as we were taught by Subir, near the zero of the chemical potential. That's actually occurring roughly here. And then at even higher temperatures, you retrieve a classical gas with, however, a quantum scattering cross-section provided by the de Broglie wavelength squared. So that's why eventually actually does go down. And of course, we retrieve happy quasar-particles at very high temperatures, namely the Bayer particles. So just to illustrate, we see those strong interacting properties in these short lifetimes in these fluids. And then there are many ways, but in particular in this talk, two ways to tune the interactions and make them strong. One is just to use a Feshbach resonance in the bulk, and the other is to throw these atoms, as we have heard before, into an optical lattice and quenching the kinetic energy, thereby realizing the Fermi-Hubbard model. Let me first talk about the unitary Fermi gas, which is really a wonderful model to try to understand all these complications, because it is stripped of many complications that you have otherwise. For example, there's no additional length scale other than the interparticle spacing, corresponding to the Fermi energy scale, and the de Broglie wavelengths, corresponding to the temperature. So there's only that. So that's nice and simple. There should be therefore a universal equation of state that many groups have measured. Especially at zero temperature, it should be even simpler. The energy has to be some universal number times the Fermi energy of a non-interacting Fermi gas, and that number comes from experiments, and it's actually very difficult to calculate theoretically. Not so difficult. It's not the worst problem because it doesn't have a sign problem, but it's still tough. One thing it tells you, if you see such an equation of state, you realize, well, there should be sound waves in this interacting gas, and those sound waves should propagate at the Fermi velocity with some prefactor, and that's precisely the thing that makes transport alive in these systems that we will study now. Just to give you a gut feeling what might happen in these gases, if you take a strongly interacting Fermi gas, spin up and spin down, and you smash them into each other at the Feshbach resonance, they basically bounce off each other, so that's how strong the interactions are. The mean free path is as short as it can possibly be, one interparticle spacing, and that tells you that the average velocity, that's going to be by quantum mechanics, given by h bar over m times the interparticle spacing. And if you ask, what is the typical diffusivity, so that would be an average velocity times mean free path, you always end up with something universal that only knows about the mass of the particles being transported. So it's h bar of that over that mass. And this is true not only for spin transport, but it should be true for charge, momentum, thermal transport, or what have you. There have been, of course, tons of experiments. This slide really doesn't do justice. I should have put all kinds of pictures of the beautiful experiments. For example, on the charge transport, using two reservoirs with a channel by the ETH group. Often these experiments have been performed in inhomogeneous traps, and that gives you a problem, a fundamental problem, that you might actually see transport properties averaged through a portion of the phase diagram. You might not actually just be in one phase, but you might actually cross through many phases as you probe this transport. Also, if you hope to measure some hydrodynamic effects, these will not be valid all the way to the edge of the trap, where the gas becomes very dilute and crosses over into the ballistic regime. That is very difficult to model theoretically. And then the spectrum of collective excitations. It's some complicated mix of the trapping frequency and the phonon spectrum at high momenta. So it's difficult to access also, strongly damped. So there comes the advent of the box, thanks to this fellow, if people recognize him, Zoran Hadžibabić in Cambridge, telling us how to make boxes, that we ought to make boxes for cold atoms. And there are many boxes around, I mean many more than fit on that slide. You will see, hopefully in this talk, that this is really a useful thing, especially for transport. But also we can hope to measure correlations, critical phenomena, precisely now that we have a homogeneous density. And some phases of matter, like this FFLO phase, requires actually particular tuning of the density imbalance that should not change throughout your system, because otherwise your interesting state would go in and out of existence through as you scan through your system. So we want to study transport, and as a physicist, the thing what you do is you just tap your glass of water and see the beautiful waves appear. So this would be a cartoon version of what we should do. Sound waves would be created, and then they decay, as you see, spatially. That decay is very interesting, because it means there must be some viscosity that makes that sound wave damp, and there could also be thermal conductivity that makes that sound wave damp, because sound also locally heats the system, and that heat spreads and therefore dissipates the energy in the sound wave. So this decay would be very interesting to measure. So we have to do the equivalent experiment to what these guys did. Wonderful. Yeah. Unfortunately, I would love to have that much lithium-6 in my body. It would be awesome. I would just swim in it. But we have to do. I was reading. We have to do this in a 100 micron size box, where the container is just laser light. So it's actually very pristine. Hopefully very low roughness also of the walls, and a good container for this stuff. Now, instead of actually shaking the walls, which we could, but it's actually nice. I like this way of just shaking the box by just ramping up and down this potential. So this is actually very nice, because what you're holding in your hand theoretically is the potential which you drive, and of course you will get a response from the gas, which is going to be in the density, which is the canonical conjugate variable to the drive, and you will therefore directly measure, for experts, the density response function as you do this. If you do that, well, it doesn't look like much. There are a few wiggles. Let's subtract the background, and then we see the sound waves, and we see indeed what you would expect in a glass of water as you tap it. The sound waves die out, and that dying out is an interesting quantity to measure. We first have fun just checking that we have sound, right? You want to see that you have a dispersion relation that's linear, and if you think back to the old times where one did Bragg spectroscopy on these trapped systems to measure sound waves on the low momentum Hogg-Hubbard modes in the Bose-Einstein condensate, you will admit that this is easier. You just tap the box with some frequency, and if there is a resonance, you get a nice mode out. Or here actually we're just tapping it 3 times, and of course we see some sound waves. We can measure their frequency and momentum.
What was the
sorry, so this is blocking, I blocked this, you don't see it, right? So it goes up to 15% of the Fermi momentum only. So the rightmost is 15%, so the Fermi momentum is up there. So it's very low K stuff. Right? Here comes a fun surprise. If you ever thought Einstein was right with his E equals mc squared idea, he was wrong. It's 9/10 actually. So we have these poster t-shirts now that we bring out. You can get one. It's expensive. It comes about because of the following. If you calculate the speed of sound squared, that should be the derivative of the pressure with respect to the density at constant entropy. And well, the pressure can only depend on things like the pressure of a non-interacting Fermi gas times some universal function of entropy. And well, we keep that fixed, so we take that out. The only reason this varies with density is because the non-interacting pressure varies with density. And we know how it does that with 5/3. And then we throw in one more thing, that the pressure is 2/3 of the energy density, just like for an ideal gas, due to scale invariance, and you come up with this formula that mc squared is 10⁹ times the energy per particle, which is something that you can measure and check out the axes. It goes from 0 to 9 here, and it goes from 0 to 10 here, so it is indeed correct. So Einstein was wrong. Oh, sorry. This is not recorded. Oh, it is recorded. Okay. So let's cut it out. This is a fun experiment where you just throw in a particular frequency and you look for the standing wave pattern that appears, and it's really fun to do. You look at these these modes, and the higher the frequency, of course, every once in a while you hit another standing wave that is sometimes nice to look at. And of course the lowest one should look, well, now it hopefully comes up here. That's the lowest symmetric one, and one more time, yeah, then this is a higher symmetric one, and so on. So you have fun with that. Summing up now over the boring direction, you get a nice pattern that you can now plot as a function of frequency, and this gives you directly, well, a sonogram, if you want, of this gas with discrete modes at low frequencies and then broader modes at higher frequencies that broaden. When you see this, you feel the urge of taking a Fourier transform in space, and you do see a happy linear relation here, as we saw before for the dispersion measurement, but you also see by eye that here there is some broadening. By the way, if you have very good eyes, you can also make out second harmonic generation in this plot. So now let's try to understand this sound, and it's basically textbook. Soon we will add some more stuff, but like we need the continuity equation. There's certainly mass conservation. We need the Euler equation, which tells us how the certain slab of fluid is pushed around. One reason is because, well, there might be a density gradient, and then the prefactor is precisely the speed of sound. But there's also a push from viscosity. So viscosity is this thing that gives you a force proportional to the gradient of the velocity field. But if you have the same gradient on either side of your slab, you wouldn't feel a net force on you. So there needs to be a curvature of the velocity profile across the slab of air. That's why here you have the curvature. And the prefactor would be, if my story was entirely correct, the viscosity. It is unfortunately not so simple. It's the viscosity with some 4/3 that you don't have to worry about, and the thermal conductivity, because of what I just mentioned before, that sound heats the soup, and therefore thermal conductivity can make that sound wave lose energy. So there are these two contributions, which for the unitary gas are quite nice to write down. So usually this is a little bit awkward expression connecting the thermal conductivity, but here you just need to know the temperature and the pressure. This gives us a dispersion relation, which is almost omega equals ck, but of course there is this damping, and the damping characteristically goes like k squared because of this curvature here. So that's a telltale sign of hydrodynamics. Let's look at these sound modes in the box that we see, the narrow ones at low frequencies and then broader ones at higher frequencies. You already see there's sort of a sum rule that these guys cannot get broader and not shrink. They also have to shrink. It's all actually in the density response function. And we can plot the width now as a function of frequency and see, well, yeah, it does look like a quadratic law, out of which now, if I just measure the damping in 1 per second and the frequency 1 per second, I simply have to divide out, knowing the speed of sound, and I get the diffusivity. And out comes, without us putting h bar in, out comes some number times h bar over m, as I promised, should be a typical diffusivity in these strongly directing regimes. Now, at that point, it's actually interesting to look at other superfluids and to learn a little bit about their diffusivities. One is, of course, superfluid helium-4. I always grew up learning that the viscosity of superfluid helium-4 should go to 0 at Tc. It, of course, doesn't. It only does if you have like narrow capillaries and the normal fluid is stuck to the walls. But if you have a big cylinder or something where the whole fluid wants to go through, you do measure, of course, the viscosity. There's always some normal fluid around giving you viscosity. And actually, the viscosity drops only by a factor of 2. This here is Tc, you barely see it kink, and then it drops by a factor of 2, and then actually rises at very low temperatures due to phonons. You're not worried about this now, but it's interesting that there's sort of a limit. You ask, what is that in h bar over m? Well, h bar over m is right there, so this has to do with the quantum limit of viscosity. What about helium-3? Because we have a Fermi system. Helium-3 actually, above Tc, is a Fermi liquid. A beautiful textbook, it's the Fermi liquid. basically. So you see that the viscosity will go like the collision time between particles, and the collision time between particles in the Fermi liquid goes like 1 over T squared. That's also what we learned in Basim's talk, what a normal Fermi liquid should do. And so they see the viscosity go up, from where actually it starts from h bar over m near the temperature where it becomes a liquid. Then it goes up to values of thousands of this h bar over m. And now what happens when it goes superfluid? Well, there is a dramatic dip. I give you that. So there's a factor of 10 roughly reduction in the viscosity. But that still brings you to that value of 1000 times h bar over m. So helium-3 is actually very viscous, which is remarkable. And well, we can understand this. Why doesn't it go to 0 or something? As long as you have this hydrodynamic description, viscosity is just always the normal fluid density times the lifetime of the quasi-particles that are carrying around the normal fluid. And it so happens that in a Fermi gas, the normal fraction is basically exponentially suppressed, because those are the broken pairs. But the lifetime of those guys, if you have them, those broken pairs, is also exponentially long. So these two factors cancel out, and you get something constant, which looks like as if you had a finite temperature Fermi liquid with a temperature given by the pairing gap. So that's why it goes like 1 over delta squared here. And that's, for helium-3, that's the factor of 1000. So what is it for us? This is a measurement of the diffusivity versus temperature in our system. It has all the scales on the order of h bar over m, and it keeps going down. And at high temperatures, well, it's not inconsistent with the limit that you expect for a thermal gas that has this unitary delimited scattering cross-section. At low temperatures, actually there's no calculation for the thermal conductivity, but you can take the viscosity, which has been calculated, for example, by Tillmann, Enz, Hausmann, and Wilhelm-Zwerger, and assume simply that the thermal conductivity in relation to the viscosity is as strong as it is at high temperatures, which is a complete ad hoc assumption, and then you get this green line. So it's clearly not a perfect assumption, but not far off. What is interesting is that nothing special happens as we cross Tc. So this is the diffusivity through Tc. The condensate fraction starts shooting up, but there's nothing special happening in the diffusivity. So that we understand now, because we have a Fermi gas, and we should not see a viscosity that suddenly goes to 0 or something like that. What then is so cool about the superfluid? Well, that's the two-fluid model. And so in 1D flow, linearized at unitarity, I can write down the two-fluid hydrodynamics equations. We again have the continuity equation. We have also the Euler equation, where, let's be careful, in the Euler equation is only the viscosity, but there's also the equation for entropy flow, which knows about thermal dissipation. So thermal conductivity is here in the equation for entropy flow. And then the last equation is superfluid flow. The superfluid flows just like a happy potential flow. And as I learned from Boris Svistунov, it really is not damped unless you have superfluid turbulence, unless you have lots of vortices that can scatter off the normal state. So this, I would say, it's the simplest two-fluid hydrodynamics that you can have. If you're away from unitarity or for helium-4, there's much more complicated stuff. There are more coefficients that come in. For the unitary gas, this is it. It's nice. What does that give you? It gives you two sound modes. Two-fluid hydrodynamics means we have two fluids that we have to worry about. The first sound is what we had looked at so far. In helium-4, it's this happy sound that basically doesn't do much as a function of temperature. And then there is second sound, which starts at 0 right at Tc, and it's basically a temperature wave now. And I can explain that best if I think about the response of first a normal liquid towards shaking, and then go to the superfluid regime. So I'll go to that description. Turns out you can write one equation that encompasses all the two-fluid hydrodynamics in the density response function. You ask, how much density response do I get for a given potential wiggle that I do with my wall? And here it is as a function of frequency and k. There are two poles that we have to worry about. Those will be the two sound modes. And I will only see those two poles in the density response if density and temperature are coupled. If density and temperature are not coupled, the density mode will do one thing, first sound, and the temperature mode will do some other thing that I won't see in the density. So I see one peak, which is the happy first sound, and nothing else. But what happens if I switch on here a non-zero delta rho over delta t, like a dependence of density to temperature? There's some wiggle here appearing near zero. Let's blow this up by dividing by frequency, which basically means I'm now looking at the step response to a sudden switch on of my potential. And you see this interesting Laurentian here, peak centered at zero frequency. That's what you always get for a normal fluid that has some compressibility in it. If you heat locally, this local heat will just dissipate and diffuse. And here comes the cool thing about superfluids. This local heating will not dissipate and diffuse, it will propagate. As a temperature wave, mostly like a temperature wave, which if there's a little bit of coupling between density and temperature, you can read it out in the density also. So that's the expectation, that you should actually be able to read out both first and second sound from this wiggling experiment. Now unfortunately this 1 over omega, if you just drive it and don't do the step response, it's down here, so it's very small. But let's see. Second sound was observed in these strong Unitary Fermi gases in a highly elongated, so quasar 1D geometry. So no doubt it exists. But now we had fun trying to do the simplest experiment to see it, which is take our box and apply an oscillating gradient to the box. Okay, so this is actually going to give us the fancy term would be AC response of the system towards this drive. And well, if you do it in the normal state and you look as a function of frequency, you see no response at these low frequencies. The first sound would be roughly here, so that's zooming into the low frequency. But if you now cool the gas, or heat it less, I should say, you see a peak popping out at low frequencies. I mean, granted, it's a bit noisy, but it is there, and you see the second sound emerge from zero frequency to some finite frequency. So this is the second sound, and if you put it in relation to the first sound, well, here's the second sound peak, here's the first sound peak, and I had to reduce it by a factor of 20 to put it on the same slide, because we're looking in the density, so clearly this is going to be highly suppressed. We're looking in the density and we are driving using a density probe, so it's doubly bad. So now with cold gases you can actually measure both the condensate fraction rather easily in this old way of ramping to the molecular side and seeing the momentum distribution of the pairs. And you can also measure the speed of second sound, which gives you the superfluid density. And the two should be related in this sort of way, and well, we have to take more data, but this looks like promising. Eventually we should see the speed of second sounds to go like this, with temperature starting from zero, should do something, and then this is the phonon branch, which honestly I don't think we will see. It's going to be probably damped like mad. The damping gets me to the outlook. For this story, I would like to measure now the damping of second sound, which was it was difficult in helium to disentangle the different contributions to the damping. We can just measure, for example, the width of these resonances or the temporal or spatial decay, whatever we want, and then therefore get access at these damping coefficients, which know about thermal conductivity, viscosity, and Boris tells me that there is no additional contribution if you don't have superfluid turbulence, which might be fun to then have superfluid turbulence and see how that affects things. If I have time, I would like to go into the lattice.
We have 10 minutes for questions.
Good, yeah.
And so if you go another 5 minutes, that'll be fine.
Perfect, yeah, thank you. Yeah. So now I'll go into the lattice, and different group of people. You might see some of them in the audience. matte today looks almost like on that picture, which was taken 5 years ago. Easier front. And the goal, of course, is to provide a better understanding of what happens in this Fermi-Hubbard model, which is simple to write, of course, especially difficult to understand. So there have been several experiments on these 2D Mott insulators. Actually, the Munich group is also now doing 2D, so I should put them on. To have these single-side resolved microscopes, and just to show off, because Rossini was such a show-off, I had to show off this thing. Okay, so if you start with this guy, 2,000 atoms, it's very tempting now to cut out a square and make a box, and that's precisely what we did. And canceling the harmonic potential a little bit, we see the Fermi-Hubbard model in the homogeneous variety, so to speak, where, of course, in the Mott insulating phase we see barely some holes. Depends, of course, actually on the interaction strength for the experts. In the metallic phase, it's riddled with holes, but it doesn't mean it's hot. It just means it's a metal now. And you can also get a metal with more than half filling. So those dark guys are the doublons that are running around. Now let's apply a gradient. We got so used to applying a gradient in the previous part of the talk. We should do that too. If you do it on an insulator, it's very boring, not so surprising. They have no way to go anywhere, so you don't see any change. Whereas the metal, of course, they all run to one side, and if you have doublons, the doublons run all to one side. So that makes sense. This is a nice way to check: do you have an insulator or a conductor? But now let's look more closely as to what happens inside this Mott insulator. I haven't resolved spin here, so I should now check what happens to spin. And spin is going to be interesting because the two spin states that we are using here in potassium-40, they have actually different magnetic moments, which is a very nice handle. You have a stronger magnetic moment here for the reds than for the blues. And so if you apply a gradient, even though on their own they would both love to go to the left side in the image, they cannot all go to the left side because the reds have a stronger magnetic moment. They want it more, right? They want it more, and so they leave the blues to the other side where the blues would actually, in principle, not like to go. So it's just due to interactions that you start to get this spin polarized state, where the spin ups are on one side and the spin downs are on the other side. That's a nice way to initialize now a spin transport experiment, because you can just switch off the gradient and watch the spin just go back to equilibrium, and that's precisely what we do. So these are the profiles. Let's just do the experiment. We start with this spin density gradient and watch it relax to 0. And the complicated thing here to understand is what's the time scale at which that happens. So theoretically, it's very difficult to calculate that. Experimentally, it's straightforward to just measure this current and as a function of time for the various interaction strengths, and extract spin diffusivity out of it. We can also check that we are in the linear response regime by plotting the current that we observe as a function of the spin density gradient that we have initially, and the field curve that we have this linear response regime. So to summarize the results on one plot, we get the spin diffusivity here as a function of T over U. So the atomic limit is over here, where you have strong on-site repulsion, and here you have weak on-site repulsion. So with strong on-site repulsion, you expect the system should at low temperature be a Heisenberg interferominute, and you have a certain prediction, that's the dashed line, what should happen for a Heisenberg interferominute. Now we are not at 0 or low temperatures. Our entropies are on the order of 1, so that's not log 2, that's 1. And so there are other channels for transport that are open, and so that's what we think is what happens here, that we get actually more than the Heisenberg result at low temperatures. It's still proportional to T squared over U. That doesn't immediately mean that it's super exchange driven. there can be two contributions, there can be many I guess, but like one contribution could be super exchanged, that particles just do their super exchange to get transport of spin, but the other could be that you have just a bunch of holes that you can fill in easily with at a rate t, which is the tunneling, but the amount of holes that you have should be proportional to t over u. But it also gives you t squared over u scaling. Now, we asked Ehsan Katami, who's in the room, to see can he actually augment his numerical link cluster expansion, which was so far used only for equation of state calculations, to also give us time-dependent calculations, and that is bloody difficult, but he managed. With the realization that he could do real-time evolution of his cluster expansion. The drawback is, well, the problem is, there's always some problem, right? The problem is here, you cannot go to very long times. So you have to use a cutoff on the order of the tunneling time, and then you might actually miss important contributions from super exchange. So it's actually impressive that just chopping off at the tunneling time, he already retrieves a third or something like that of our observed spin diffusivity. But if you did this on the Heisenberg model, it would suppress, of course, the spin diffusivity quite a bit. Okay, this is just a zoom in on the temperature data. Basically, to summarize, here we see a spin diffusivity. You could write it if you wanted to as h bar over ms, where ms is sort of the mass of the spin that's transported. To be honest, this is just like, it's basically the definition of ms, because what we see is just some slope proportional to t squared over u times the diffusivity of a bare fermion. Whereas over here we approach the charge diffusivity, where it's really single holes basically moving around. So that's what we think, that we have spin transport due to both super exchange and double hole resisted tunneling. We can also directly measure the spin conductivity, and that gives us this graph. The story is pretty similar, just wanted to tell you that you can get the spin conductivity from the Einstein relation, or you just directly measure it. Either way gives you the same result. The two ways are the red and the black data points, and we find the spin conductivity that goes like T over U with a prefactor. This is just showing the spin susceptibility that matches thermodynamics. This is to summarize. If you have strong interactions, you get short-lived particles that are no longer actually quasi-particles. The quasi-particle description breaks down. You often get things like a diffusivity that goes like h bar over m, but of course the m can be very different for the different types of transport. And I think this microscope, these microscopes are very good to measure these transport coefficients. Here's an outlook. We want to measure AC conductivity by just shaking our gradient, just like we did for the density in the unitary Fermi gas, and we see, well, we get a response, very nice, and now that should be now measured as a function of frequency to see what's going on at finite frequency. So with that, I thank you for your attention and thank my group for their hard work.
We have time for a few questions from Martin.
I have a question about the box potential part. So because here we have a finite size of the box, so it's kind of like we put some cutoff on the allowed momentum, right, of the solar. So I was wondering if somehow you can change the distance between these two barriers and move that cutoff higher and higher.
Yeah.
Do you expect that? Maybe change the dynamics, maybe even change, I don't know, like the critical velocity, because you don't have a more momentum, lower phonon mode and no momentum, something like
Right, yeah. So in the bulk Fermi gas, we have a box size of 100 microns, which is maybe 300 times the sort of coherence length in the particle spacing, so that should be sort of safe. We don't worry about being limited by the cutoff. In the box of the Fermi microscope, we check the length and check that it actually the diffusive behavior is scaling correctly with the system size squared as it should be if you change your box size. But I admit we are limited in the number of rows that we can make.
So you've also checked that you're in the linear response regime with the amplitude shaking?
Yes, so that's That was on a slide that I could dig out again, but like, yeah, we checked that we had a response.
Others? Yeah.
So I'm not sure I completely follow the part about the spin diffusion. So you first have the gradient and you prepare this, let's say, state in which all spin up on one side and the other. Then you reduce the gradient to allow this diffusion, correct? So now the gradient at which you, so the value of the gradient at which you see diffusion structure is not also a way to measure diffusion.
The gradient at which we see diffusion. So we would say we are in the linear response, so it wouldn't matter so much which gradient we use. At some point, of course, if you do too little, you don't have a nice measurable spin density gradient. But let's say we do a healthy one that we actually see some signal, and then we suddenly switch it off. We don't slowly switch off, we suddenly switch it off, and then watch the diffusion.
Yeah, but if you don't suddenly switch off and you smoothly change, and at some point the critical gradient will tend, or not,
Yes.
critical value of the gradient, which will be a direct measurement of the spin-spin interaction, something like this.
Yes, so let me try to rephrase a little bit into this. So it's almost going to the AC spin conductivity, where you have a gradient, but you slowly, or whatever, with some frequency, you go up and down, and you see, does the system follow? At low frequencies, it'll follow the applied gradient, but at high frequencies, at some point, there will be inertia, as Wasim had talked about. There needs to be some collision time before they can actually follow, and that's a very interesting thing to measure now. What's this collision time? What's this inertial time? So that's what we want to measure.
Okay, yeah.
Martin, so very nice. What about to measure the speed of sound and the physics in the BCS? So would it be possible, because I guess that the damping of sound wave there should be affected by the BCS?
Yeah.
I guess.
Yeah, I would.
Which is the limit that you can think about?
I would love to do that. I think it should be a beautiful experiment because on the BCS side, TC is very small. So there will be hopefully a large range where you will see Fermi-liquid behavior. So it might first go down to h bar over m, then it will grow like 1 over t squared, just like in helium-3, and then we should see a rather dramatic demonstration of superfluidity already in the sound damping. It should suddenly go down just like in helium-3. I would love to do that, yeah. Should be cool.
Okay, last question, Carlos.
Very quickly, Martin, could you put back the plot for the second sound, the historical data?
Maybe this one?
I think there's another one. I saw somehow some no, not this one. The one that has some oscillations. Yeah, if I look at the thing here, I don't know. I'm not an expert, but I look at some oscillations that I could put some other things there. Do you think there are other things that you've seen?
There shouldn't be. So hydrodynamics should be awesome for any superfluid. So that's why we don't, give like an arbitrary function to fit to this thing, but we give something that we expect should be good. So you're saying we should clean up our data?
In the right frequency. No, okay, but I mean, so those things are the right frequencies that you would expect.
Yes. That I show here when I compare the speed of sound versus condensate fraction, and take some rough idea of how they should be related. It sort of matches, but it's not enough data to do a good job.
Just a quick thing. For the Einstein, when you compared in the lattice case, there was this Einstein relation, the direct measurement. There were also some big differences as sort of towards the end, at the high. Yeah.
I love it. You have these sharp eyes. You find everything that we want to hide. You're saying this guy, that guy. Yeah, I mean, look, within the error bars.
Yeah, it's huge. It's a factor of 3 or something.
Yeah, it's a bit tough because things go so fast, right? That the current is actually quite right. And okay, so you say we should spend more time on that. Yes, you may. Yeah.
No, so when you present it, you get an average of those?
Next time I'll show the slide until.
We've got to stop there. So let's thank you.